starting to look at how we handle accelerating motion in 2 dimensions. And really, excuse me, the prime example for this is projectile motion. Okay, regardless of what object we're talking about, all projectiles have a few similar trends. First of all, they all follow a parabolic path. All projectiles only have the force of gravity acting on them. Only gravity acts on them. And air resistance, but we ignore that. Okay, because we're not going to be throwing anything fast enough for air resistance to matter. Okay. And lastly, we've already identified some traits of projectile motion, like when you throw an object straight into the air, the velocity at the very top is 0 in the y dimension. But we've also started to put together that the velocity at equal heights has equal magnitude. Velocity at equal heights has equal magnitude. What do I mean by that last statement? So for any object that we're tossing up into the air, if I pick a certain height, I'm just going to say height h. The velocity at this point and the velocity at this point will have equal magnitudes, meaning they'll be moving the same speed, but note that because it's velocity, I'm just saying magnitude, the direction is going to be different. So the direction has varied, but the speed is the same. Good with that idea? Okay. So let's look at actually solving for something that's been thrown. So let's start just an easy example here. Page. If a baseball is thrown horizontally at what's standard baseball speed in the majors? Like 100 miles an hour? Yeah. 96? Okay. So we're talking probably close to about 50 meters per second. If baseball is thrown 50 meters per second from a height of average pitcher's height, probably going to be 4.5 feet to their arm. 5 feet to their arm? Oh, they release high? All right, so let's go 7 feet then. So 2 meters. We want to know how far will the ball travel before it hits the ground. Will the ball travel before it hits the ground? Okay, so just starting out, dices, draw, identify, convert, equation, solve. First thing, I'm just going to draw out what we've got here. So we've got our stick figure guy, he's throwing a ball, and it drops there. Now, a couple of things that I want to point out about my drawing. This curves immediately. This is not flat for any period of time. Okay? As soon as that ball leaves his hand, it starts dropping. So it's one of the shortcomings of my ability to draw here. And actually, you saw that on the FCI. There was, I believe it was a cannon problem, and it asked which of the paths was the path of the projectile. Well, as soon as it leaves the cannon, it has to start dropping. In the same way, as soon as this baseball leaves his hand, it starts falling. Not even assuming. We said it is. Okay? All right, so draw, identify. What variables can we identify here? All right, height, which is 2 meters. What else? Say again? Acceleration, negative 9.8 meters per second squared. Anything else? VI is 50 meters per second. Do I know any other details? No, not at the moment. All right. However, the way we're going to handle this is we're going to break this into directions. So we're going to look at this in terms of the horizontal dimension and the vertical dimension. So horizontal, vertical. Let's start with the vertical because that's kind of similar to what we've been doing. And I'm going to have VI, VF, A, D, T. What variables can I identify from our situation that exist just in the vertical dimension? Acceleration, there's our 9.8. Anything else I can identify just in the vertical? Distance, and I'm going to make this negative 2 meters because the ball is going to come down 2 meters, right? There's one other that I can identify from the vertical. Why? All right, so there's no initial vertical velocity. It has to start dropping once he throws it. Good. All right. Now, how about my horizontal? What variables am I going to be able to identify here? Okay. Do I know anything else? Distance we're trying to find. Is there anything causing an acceleration in the horizontal dimension once that ball leaves his hand? No, nothing. But we're going to neglect it because we're not working with something that's significant enough on that. I mean, yeah, air resistance is why we get curveballs, but we're not talking about a curveball yet. All right, and time. So I want you to notice that in our vertical dimension, we've identified 5 potential variables, whereas in the horizontal dimension, we've only identified 3. Okay? Now, for those of you who said that, yes, one dimension does affect the other, here we'll throw you a cookie. Time in one dimension is always the same as the time in the other dimension, because how long it takes to fall is how long the ball is going to be in the air, so that determines how long it gets to travel. However, again, the velocities here do not affect the velocities here. Okay? All right. So, from here, if I want to know how far it'll travel before it hits the ground, what variable do I need to know in order to solve for my horizontal displacement? What variable do I need to know in order to solve for my horizontal displacement? Time, good. So, and since we just declared that time here and time here are the same, I can go about determining how long the ball is going to be in the air so I can determine how far the ball is going to travel. Okay? So, over here, if I've got VI, AD, and I'm trying to find T, I'm going to use D equals VIT plus 1/2 AT squared. I picked that one because I don't have and don't care about VF. Okay? So negative 2 equals 0 plus 1/2, negative 9.8 T squared. Negative 2 over 4.9, negative 4.9, equals T squared. And what is the total time that the ball is in the air? Someone with a calculator. Say again? 0.64 seconds. Anybody confirm that? Yep. Okay. All right. So I think I had 2 people say that that was good. All right, so 0.64 seconds, since that's our time value, I can now put that up here as well. Okay, and now solving for the horizontal displacement is pretty easy. 50 times 0.64, and we're going to get something like 36, 2/3, 33. Somebody want to find that exact value for us? 32. All right, 32. Anybody agree? 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 All right, excellent. So you guys have just walked through your first projectile motion problem. Now, what this is doing is it's describing the motion of any object that can be thrown, launched. Basically, as long as it doesn't have a rocket attached to it, we can use this process to describe the location and motion of any object undergoing projectile motion. Okay, let's take another look at this, but we're going to change up one piece here, and that's we're going to adjust the path of this ball because, let's be honest here, chances are he didn't throw perfectly horizontally, right? So we're going to arc it up just a little bit. And we want to know if he angles the throw, and we're going to angle the throw at, let's go 15 degrees. So if the throw is angled at 15 degrees, does it hit the ground at a shorter distance or a further distance? If the ball is thrown at an angle 15 degrees above the horizontal, does it go further or fall shorter? Okay. So, approaching this problem, what do I need to change about my identified variables? What do I need to change about my identified variables? Okay, I need to break into my initial horizontal and my velocity. So we've got now a velocity that uses this 15-degree angle and still traveling at 50 meters per second, but no longer is all of that 50 going in the horizontal. Some of it's now going in the vertical. In order to determine how much, we need to use that vector addition stuff that we had last week in order to figure out how much is going horizontal, how much is going vertical. So using the pair of trig functions, we can find our horizontal and our vertical. Can someone break that down for us?
Height is 30.5.
Okay. And the horizontal? And does someone agree with Ed's numbers? 38? Round it up, okay. Do I have somebody agreeing with Carter's number? Yes? And somebody with Ed's? Okay, excellent. All right, now that we've re-identified our horizontal velocity and our initial vertical, I want you to go ahead, take a moment, and answer the question. Does the ball hit the ground at a shorter displacement or a further displacement? We're in radians, huh? So vertical, all right, and how much? There we go. Thank you for piping up those who didn't agree. I was going to say, that looks like it's closer to a 45-degree triangle than a 15. All right, so 15 degrees. Now do we agree with these two values? And we're all in degree mode? All right. Let's go ahead and try to answer that question. Your variable identification should look something like this, with the horizontal velocity being 48 meters per second. Displacement, we don't know. Time, we don't know. And vertical, we're going to have VI is now 12.9 meters per second. VF, we don't know. A, negative 9.8 meters per second squared. D, negative 2 meters. And T, we don't know. Hopefully you've got that spot reached. If you haven't, well, let's take a closer look and keep going. Okay. In order to find time, many of you have probably already looked at it and said, well, D equals VIT plus 1/2 AT squared. Well, therefore I can fill this in and say negative 2 equals 12.9T plus 1/2 negative 9.8 T squared. How many of you got to this point and then went for the quadratic equation? Okay, that is one way to solve it. Your answer that gives you a positive time would be the right one. The answer that gives you a negative time would not be useful. Okay, that's one way to solve this. The other way to solve this, and the way that I'm going to do it, is I'm going to find VF first. I'm going to find VF first and then go through and find time. Is that how you did it? Yeah. Excellent. All right, so I'm going to say VF squared equals VI squared plus 2AD. I'm doing this way mostly because I hate using the quadratic equation. So VF squared equals 12.9 squared plus 2 times negative 9.8 times negative 2. Okay, I can plug that into a calculator, square it, and I've got my VF. This is also a useful way to do things because the AP tests, my free response questions, book questions have a tendency to really like multiple parts, and finding the final velocity is usually one of those parts anyway. What did we get for final velocity if we do the math on this? $14.3? How many people agree? Okay, good. What if I told you no? Anybody know why I might tell you no? Say again? Needs to be negative. There we go. Object's moving down at that point, right? So when we take the square root of 200, it's plus or minus 14.3. We know we need to take the negative 14.3 because at that point the ball is moving down. Okay, and then I would follow through with VF equals VI plus AT. Negative 14.3 equals 12.9 plus negative 9.8 times T, and I can find my time value. So negative 27.2 divided by 9.8, I'm going to get 2.65. 2.76. Thank you. How many people agree? Those of you who did the quadratic equation, is that about the same time? Okay. They may vary due to significant figures and how those are carried, especially since we square rooted a couple things. But it is effectively the same time. All right, now we can use that up here. 2.76 seconds, and it is significantly further that this object travels. Okay, so we are looking at 140-ish? 133? All right. Questions on solving a problem like this? Okay. Next pieces doesn't make sense. How many of you have played baseball, softball, something to that effect, sometime in your existence? Really? Okay. There we go. So if you're in outfield, do you throw the ball straight forward to get it back to the inner field, or do you arc it up? You arc it up, right? So next piece here, and this is actually a useful piece for your projectile launchers. 45-degree angle for release is going to give you the greatest total displacement. Objects released at 45 degrees travel the furthest horizontal displacement. Now that is in the absence of air resistance. Some of them can vary a little bit by a few degrees, depending on how fast the object's moving. Okay. Questions on that statement? Okay. All right. So I'm going to look at a separate problem here. If you guys haven't figured out yet, I'm not a terribly nice person, and I make fun of my students way more than I probably should. So we're going to put Admir at the top of a cliff. And Braden's going to push him off. All right, so first piece here. Admir is going to hit the dirt at 5 meters away from the cliff. Okay? And we're going to say that Braden pushed him. Admir was pushed at 2.3 meters per second. How tall is the cliff? Okay. Use the same approach. He's going to be in projectile motion because once he's been pushed, what's the only acceleration that's acting on him?
Gravity.
Gravity. All right? So he's going to follow a parabolic arc. He's going to accelerate due to gravity. We're going to ignore air resistance. We can separate our variables into horizontal and vertical components. And go ahead, see if you can determine the height of the cliff. .17. All right. And then in the vertical, what values did you have? T. All right. We just got it. 2.17 seconds. Acceleration, negative 9.8. Initial velocity, how much? I heard final velocity? That's a separate situation. So what we'd be looking at then is if we had an acceleration versus time graph, we'd be looking at gravity, 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 hit the ground, some high positive acceleration. We are only looking at this segment here. Okay? If we started to look at this segment there, we'd have to know how long it took him to come to a complete rest. So really, if you want to consider it up until the instant before hitting the ground, that may be a better way to consider the situation. All right, we don't know. And displacement, well, that's what we're trying to find. All right, this looks like D equals VIT plus 1/2 AT squared to me. Yeah? All right. So D is equal to 0 plus 1/2 negative 9.8, 2.17 squared. And what did you guys get for height of the cliff? How much? Yeah? All right, so 23 meters for a cliff. Questions about working through this problem, solving this problem? All right, I've got one more that I'd like you to do today. And since we were just talking about it, let's go ahead and work with this one. We've seen my terrible airplanes before. And we're going to move forward at 500 kilometers per hour. Okay? And we're going to have the plane be at 10 kilometers in height, so 10,000 meters. Not really. That'd be like, well, 10 kilometers is like 5 miles. So 5 miles is 25,000 feet, 25 to 30,000 feet. That's standard cruising altitude. All right, traveling at 500 kilometers per hour. And we've got our target here. And we're going to say that we are some distance out. Okay. A crate is dropped from the plane and needs to hit our target exactly here. Okay. We want to know how far in advance, what distance from the target do you need to drop the box out of the plane? So this is actually a rather realistic problem in terms of a couple of things. This is a technique used for dropping bombs, alternatively dropping medical supplies or other supplies into locations that you can't land. Something that's used very frequently by different groups. I don't exactly know how to classify them. Not an unrealistic problem, actually. Go ahead, see if you can work through it. Find D. I strongly suggest by beginning to identify your variables in the horizontal and the vertical, and then probably use it finding time.